Hi everyone. Welcome to this live stream. Today we are looking at electricity and magnetism. So what I've done, I've gone and found some questions from different years and we're going to be working through them. I chose questions that would give a good spread across different topics in electricity and magnetism. So I do hope that by the time we are done tonight, you are feeling very, very, very confident going into your exam. Hi, Michael. Hi, Casey. Thanks for joining. Hope you guys got some rest today. And hope you are ready to go into this work that we're going to put in right now. So I'm going to share my screen. All right. So let me know as soon as you are seeing my screen so that we can start. Good night, Doral. Doral's Online Academics. Good night. Are you seeing my screen? Anybody see my screen? Okay, awesome. Thank you. So now we're going to start with this question that's on screen, and it's the 2018 question. And we're going to start with this one. So let me zoom in. And we met this question while we were doing our last question in the 2023 paper. So this one, we know the answer for this one. We defined it as, so electric field is the region around a charged object in which another charged object will experience a force. So I'm going to jog your memory a little bit by going back to the one we had. Where is it? Right here. Okay, awesome. Okay, awesome. So let me just get back here and tag some of these lovely responses. It's kind of blurry, Michael. Leave the live and rejoin and see if it works better for you. So a region around a charge, yes. So this answer is in 2. So a region around a charge, body where an electric force is experienced also. So why is this not loading now, Lord? Ooh. So I'm going to stop sharing and see if it comes back up. All right, so I'm going to probably have to close Microsoft and go again. So we can look at you can start sending in answers for the next question, which, where are we? The next question now is asking about the direction of the magnetic field, the electric field rather. What's the direction of the electric field? So we have a parallel plate, and how does Casey, I'm not able to use a higher quality because StreamYard doesn't really give me that option. When I'm posting, I usually use that higher quality, but when I was setting up, I didn't get a quality. Let me see if I'm seeing it. I didn't get a particular quality for the output. Let me see. Well, I'm seeing it, but I can't edit it, so maybe that's a fault. So I can't update it at all. All right, so maybe what I'll do next time I go live, I'll check to see if I can set the quality at a little higher than 720 before I complete the setup, because I'm not getting that option at all. All right, so we're not supposed to go and check back the other question because it's not loading. Arrow should go towards the negative plate. Very good. The arrow moves from positive to negative. Yep. Yes, it does. So let me put this one up. Yes, it does. My page is back up now. So I can start sharing again. All right, good. So it says we should draw it. So do not be afraid to draw on the exam paper. Don't take extra paper and then draw it on your exam paper. So remember, we would have established how we determine the direction of an electric field, and that's the direction a positive point charge will go if you put it in that field. So naturally, we know that like charges repel. So we are going to have it moving away from positive. And also remember that for a parallel plate, that's the pattern for the field. So this question is worth 2 marks. You're getting 1 mark for the pattern and 1 for the direction. So now we go on to the next question. A lightning strike is an example of an electrostatic hazard. State one other hazard of static charge. So we have lightning as one. What's another hazard of electric charge? me look to see what responses you are giving me. So what's another? Do we know lightning is one? What's another hazard of electric charge? Or static charge rather? Hazard death, charging from fabric in the seat of vehicles. Right, good answers so far. Death is definitely one hazard. And the shock, as in electrical shock, is also a hazard. And the hazard that you can get, yes, Daryl, yes. So the shock you will receive is, it's not going to be, or may not, it depends on how many charges you're talking. It's not going to be as hard as if you get an electrical shock from, say, an electrical mains, but it can still be very much of such that you will really feel a good tinge. I don't know how many of you have ever, maybe if you're pulling out, the times I experience that kind of shock most is like if I'm pulling off a garbage bag from the roll, what I will find is that you hear that static clinging, you're hearing the static charges making that popping sound, and then it has never given me a real pinch, but yeah, it's there and I'm aware that it is there. So that's definitely one hazard of static charge. So electric shock. And as Daryl said, one useful application. Where is it? Where did I see that? Dust extraction, good. And photocopiers. Casey said photocopiers, good. So any of those two, and you have other applications too. You have electrostatic spray painting, you have crop spraying, any of those will do. It says one, so you don't have to go and be thinking how many you need to put. Just one works. So let's put electrostatic. I'm gonna give you more options. Dust extraction, photocopying, crop spraying, and the list goes on. So now we come to this question. It says the graph in figure 4 shows the alternating voltage output from a generator. We can see what kind of graph is this, or what kind of, even though they said it, I'm still asking just to see if you are following what was said. What type of current would this be showing? We're seeing voltage and time. What is the source? The source of this one. So once you see a graph like this, it's telling you that it's what kind? AC. Excellent case here. So this is definitely AC. Once you see it changing between positive and negative, it is AC. So the graph question now says, use the graph in figure 4 to determine the value of peak to peak voltage. So peak to peak, it's going from peak to peak. So what is the voltage as you go from this down to this? How much volts is this spanning from peak down to peak? Good, Daryl. AC, yes. So peak to peak, what's the voltage? Good night, Jaheem. What's peak to peak? Excellent, Daryl. Alternating direction, awesome. Fatima. All right, so 10 is peak. 10 would be the peak voltage. Same, likewise, Casey, 10 is the peak voltage. But they're asking, what is the voltage this way down to here? Because this is one peak, this is one peak. So what is this span? Hopefully you can see it. I use black as well. Let me use a different color so you can see where I'm drawing. So here, what is the voltage as you go from peak down to the next peak? You have to do the sum. So as you rightfully say, from this side to this side is 10. And if you checked from this side, it would also be 10. So what is the sum? Elena Preston, I'm thinking when you did it, there you go. So even though you have positive 10 and negative 10, you actually are just going to add 10 plus 10 to get 20. So you wouldn't say 10 minus 10. No, it's going to be 10 plus 10, and that would be a value of 20 volts. Back to my black ink. All right, good. Then it's the next question asks for the period of the alternating voltage in seconds. Now, the main fact that they specified in seconds, it means you now need to go back to your graph and see what is the unit on the time axis. What's that unit? MS. What does MS stand for? What is MS? What unit of time is that? Milliseconds. Excellent, Chrissy. So the time axis is in milliseconds, and they're saying to us, I want you to give me your answer in seconds. So first thing we need to do is to find the period. And what is the period? Period is the time taken for, awesome, Casey, milliseconds. Period is the time taken for what? All right, what is the period? The time taken for what? One complete oscillation. Good, Fatima. So it simply means then we identify one oscillation. Look at it. I'm going to trace along, might not be exactly along it, but you'll get the gist. So we can identify one oscillation by the point where the graph starts to repeat itself. So at this point here, we are going into a crest, coming down. We are not going into a crest at this point, so we have not completed an oscillation as yet. Going down to the trough, and at this point, we are going into another crest. So this represents one oscillation. So go again. We can identify an oscillation by tracing along the graph, and we're from your starting point where the graph starts to repeat itself. That is one oscillation. And that's period, the time taken for one complete oscillation. So good A, very good A, one complete oscillation, right? All right. So then what is the period? What's the time there? For one oscillation, we're starting at 0 here. What's this time? Eight milliseconds. Excellent. Excellent. So here, let me just write the answer. It's 8 milliseconds. Or you could write T equals, period is capital T, 8 milliseconds. But guess what? They said they want the answer in seconds. And Daryl was right. He gave us the method to convert already. He said to convert, you divide by 1,000. Awesome. So I'm going to divide by 1,000. I'm also going to write it as standard form. So 8 milliseconds. Good. So that can either be, T can either be equal to 8, can put 0.0 times 10 to the negative 3 seconds, or 8 divided by 1,000 would be 0.123 seconds. So that would be your answer. Either you put it as standard form, 8 times 10 to the negative 3, or you put it as a decimal, 0.008 seconds. All right. And then the frequency of the alternating voltage from the supply. Now the frequency is related to the period. So F is equal to 1 divided by the period. So we now substitute our values. F is equal to 1 divided by 0.008 seconds. What's that equal to? Where's my calculator? Right here. Anybody got the answer yet? Quick fingers. Who has quick fingers? 1 divided by 0.008, yes. What's the answer? 125. Awesome. 125 hertz. And that was Elena gave us the answer first. 125 hertz. Good. The symbol though, Elena, it is a capital H and a common Z. And Daryl is the one who gave us that correct unit. So remember, you must have your correct unit to get your maximum marks. If you don't have your correct unit, then you're putting yourself in problems. You would have done what you should have done, but because you're not putting your correct unit, you're losing marks. And the case of the letter is indeed important. All right, awesome, Daryl. So another way could be 125 per second. But remember, we mostly stick with our SI unit unless otherwise asked, so we can leave our answer in hertz. And that would round up this question. And for this one, we would have gotten our 2 because they first want you to read from the graph, that's your mark. And to get the correct answer, that is another mark 2. For this one, they want us to read from the graph to get 8 milliseconds first, yes. And then write it in seconds, that's 2 marks. And for this one, 4 marks. They want us to have our formula, substitute, but apply what we got from the previous question. Write our answer with units, and that would be our 4th mark. So we would have done all of that. And let's go back over here. We define electric field. 3. We drew on the diagram, like I said, 1 mark to get the pattern, 1 mark to get the direction. So that's 2. This one, state 1 hazard, electric shock, that's 1. This one hazard. Oh, we did more than they asked, so that's another one. So we get our full marks there. So we're going into our next question now, which is magnetism. Good stuff. No, this is still electricity. This is transformer. So it says the transformer is a commonplace technological tool used in our daily lives. Figure 6 shows one type of transformer used in electricity distribution. State the name of the parts labeled A, B, C, and D in figure 6. Let me see. So what is A? Primary coil. Excellent, A. I like your name, you know. It sounds like you are saying. And Fatima got it first. And Casey also got it. Sounds like you're saying, you know, I'm just going to ace this thing. Good job. Good job. So A is primary coil. What's B? What's B? Soft iron core. So Fatima, to be more specific, you would say soft iron core or laminated iron core. But we wouldn't use solenoid for this one. So yes, I got Kasia, Elena, and Chrissy. Awesome. So I'm going to put laminated. But soft iron core would give you the answer as well. C would be, what does C look like to you? AC supply. Good job. A, finish it off though, not just AC, but AC supply. Fatima, say supply. It's the AC supply. Kasia is already on a roll. She gave us D. Good job. So this is our AC supply. And of course, Kasia would have already given us, this is our secondary coil. And that wraps up that question. So, of course, we did our due diligence, so we get our 4 marks. All right, so now we go to the next question. Identify the type of transformer shown in figure 6. What type of transformer is that? Step up, excellent. It is a step up. So Elena got it first, then Fatima, then Chrissy. Awesome. It is a step up transformer. How we identify step up? First thing we need to do is to identify where the source is. Where the input is, we need to identify that. Once we identify that, we can know that this is our primary coil. Now, to know if it's step up or step down, you look at the number of turns on primary and the number of turns on secondary. If primary is less than secondary, it is step up. If primary was more than secondary, it would have been a step down. So because primary is visibly less, then this would be a step up transformer. And then now state the formula that relates voltage to number of turns in a transformer. What formula is that? And I know you won't be able to put the subscript, so you can just write them beside each other. I'll know what you mean. In terms of the P and the S, you won't be able to write them as subscript in the chat, but once you write them, I'll be able to decipher. Okay, awesome, awesome. NP. A check. A check, you have something. Oh, you corrected. Awesome. Chrissy, good. Atima, good. Very good. Casey, very good. So, A, I'm not going to put up your first one because that one was not so, I know it's a typo, but you corrected it good. And Fatima, and then you got this part right. Good job. And then Casey. So very good. So once we're dealing with number of turns and voltage, primary, if primary is in numerator, it's numerator for both of them. And the same goes otherwise. So it's NP divided by NS is equal to VP over VS. And once we do that, we get our 1 mark. Awesome. So we've done that part. We're going to the next part now. A transformer has 5,000 turns in its secondary coil and 50 turns in its primary coil. The voltage supplied to its primary coil is 12 volts AC and a current of 6 amperes flows in its primary coil. Calculate the power input of the transformer. So we're going to record what we got first so that we are making sure that we have, and remember it's a step up. So that should help you to not write the wrong things. And I'm going to show you why. So just to avoid confusion, it says a transformer has 5,000 turns in its secondary coil. So I don't want anybody to get nervous in the exam and just see 5,000 first and think it is primary. You have to try to remain calm and remember that, okay, this is a step up. So the number of turns in secondary should be greater. And then it tells the number of turns in primary is 50 turns. And it says the voltage supplied in its primary coil, so VP, is equal to 12 volts. And the current in the primary coil, so that's IP, is equal to 6.0 amperes. So now we are asked to calculate the input power of the transformer. What formula will we use here? Input power, which equation will be applicable for power for this one? Awesome. A, P equals IV, capital P though, is equal to current times voltage, and that would be 6.0 amperes times 12.0 volts. And remember, you have to use, it says in the input, so you have to use the values from primary. Even though we don't have secondary, but just in case a question comes where they're trying to throw you off, make sure you are using the input. So primary values to calculate it. 6 times 7, 6 times 12. Last time I checked, it was 72, right? So it was 72 watts. Awesome, Chrissy. So now we go to the next question. The voltage across the secondary coil. So we have number of turns for both primary and secondary and voltage of primary. So we can use those in our equation. So they said voltage in secondary, so I'm going to put Vs over Vp equals Ns over Np. And it doesn't matter whether you have primary in the numerator or secondary. Just make sure if you have primary on as numerator on one side is primary on the other side when you're dealing with number of turns and voltage. So I'm going to transpose. I need to get rid of Vp. So I'm going to multiply both sides by Vp. So we have now secondary voltage is equal to Ns times Vp divided by Np. Draw my line, go to the next side. So number of turns in secondary is 5,000 times voltage in primary is 12. And this is turns divided by, put my equal sign. Number of turns in primary is 50. So if I divide 15 to itself 1 into this 1, make sure that 0 is marked out. So that would be 100. So that would be 100 times 12. 1200 or 1200 volts, because turns will be cancelled as well. Awesome, Casey, awesome. So that's 1200 volts. And the final question now says the maximum secondary current if the transformer is 100% efficient. Now, if a transformer is 100% efficient, what does that mean? For a transformer that is 100% efficient, what does that mean? A transformer that is 100% efficient, what does that mean? Right, so just waiting to see if anybody else. No, current is not lost. Hi, Brianna. Yes, current is not lost. Good, good, good. Very good. And we refer to them as an ideal transformer as well. So for an ideal transformer, we say that power in the primary is equal to power in the secondary. Awesome. So we already calculated power, didn't we? We calculated the power in the primary. So we did this. So because this is asking us for a transformer that is 100% efficient, the power that is in the primary would be the same power that is in the secondary. So the maximum current, secondary current, if the transformer is 100% efficient, good, you can use the equation power equal current times voltage. Do you know secondary voltage? Yes, you do. And do you know the power? So what we're solving for is current. So current would be equal to power over voltage. Right? So let me just fix up the current is not lost. It's actually power that's not lost. because the formula for power is current times voltage, and we know that for a step up, voltage is going to be higher than voltage in primary or current. So let us do the question and figure that out. So let's go. So current is equal to power is what? We worked out the power to be 72 watts. And that is divided by the voltage, which is 1200 volts. So let's see, what's that answer? 72 divided by 1200. So what's the answer to that? 72 divided by 1200. Good, 0.06. So now you're getting exactly what I was saying. So you realize that the current has changed because the current in the primary was 6.0, but in the secondary, it is now 0.06. So as I was saying, it's not current that is unchanged. It's your power. Power remains unchanged. And that we can use reasoning to figure it out because, like I said, if power in the primary is a certain value, the current in primary and the voltage in primary will be of whatever value they are. Now, when you go to secondary, especially for a step up, the voltage will be higher than the voltage in the primary. So that means for you to get the same power output as input, your current has to be lower. So it's a kind of inverse relation between the current and the voltage for the transformer. That, and just a side note, that's why I would have said when you're doing your formula, you just make sure that between the number of turns and voltage, if you put secondary in the numerator, it should be secondary in the numerator for both. And same if you write it where you had primary in the numerator, for number of turns, it's the same for voltage. However, for current, it is an inverse. So for current, whatever you have in the numerator for number of turns and voltage, it's the opposite for current. So current will be, in this case, primary in the numerator, secondary in the denominator. So those are things that you can look out for, and this is your equation that you use for transformers. So just our grade check again. We would have done our due diligence here, 4 marks. We would have done our due diligence here using our formula, substituting an answer with unit, 2 marks. And this one, we did our formula, we transpose our formula, substitute, and our answer with unit, 3 marks. So we are done with this question as well. We're not doing too badly, we're done 2 questions. So now we're going to another one, which is June 2022. Okay, Chrissy. Just seeing a question, but I see that you got your answer. Awesome. So let's go now to our next question. And this one is June 2022. So it says complete table 5 by inserting the missing electrical circuit symbols and their names. Filament lamp. I mean, you can't tell me that, so I'm going to have to just draw that. There is no way for you to, unless you're going to get very creative and put it in the chat. There is no way for you to represent that one in the chat. So I'm going to do that one. Maybe what you can do is to tell me the names that you can do. So this one, get my black ink. So the lamp has a little swirly, too big. But anyway, you get the gist. And a circle around it, that's your lamp. What is this one called? What's the second one called? Diode, excellent. Good, so A got it, Fatima got it, Chrissy got it, Casey got it, Daryl got it. All right, so Elena gave us an answer that I want us to consider. We have here a semiconductor diode. Tom, tom, tom. And she can actually go. Sometimes though you will see a semiconductor diode having a circle around it. Sometimes the diode too will have that. Not a problem. But it's a safer bet to say diode. You won't get marked down for it, but it's safer to just say diode. But if it's a semiconductor diode, they won't mark it down for that. So sometimes you'll see the semiconductor diode like this. So it depends. Different applications sometimes have different. Fuse. I saw something about fuse a while ago. Fuse is like a rectangle with a line through it. Awesome. Yes, it is. And there's another symbol too. Not one that we use quite often. That's a fuse. Don't confuse it with a resistor, please. Do not confuse it with a resistor. The resistor doesn't have the line going through it. The fuse does. And this is the other symbol. Something like that is the fuse as well. What's the fourth one? Fourth looks like an AC supply. Excellent, Daryl. High PR squared. It's an AC supply. And I'm going to show you why it's an AC supply. I'm going to show you. So a switch would look like this. More or less. That line looked like it went a little high. But the AC supply now, the difference is it has a little squiggly that resembles a sine wave. So the AC supply will have a symbol looking like a sine wave. That's the difference. And that's it. So 1, 2, 3, 4. It's 6 marks. There's nothing else to fill in. So we would have gotten our 6 marks. Now this one here is a little off because these are not cells. These are variable resistors, so this is not a cell. So that's a thing for the question. You have to look out for these things. Sometimes, there is a little error, but I didn't ask you to do anything with it, so let it be. Let it be, let it be, let it be. Yeah, it does look like a switch, but like I said, I showed you the difference. So, looks like an AC supply right there. Right. Yeah, PR squared. So it does look like a switch, but you have to look for that little sine wave in the middle to tell the difference. All right, so let's move on. If the standard charger can deliver a current of, the manufacturer of a popular cell phone has upgraded the battery capacity to 9,600 coulombs. If the standard charger can deliver a current of 0.8 amperes, calculate the time taken to charge the battery. So we have charge here. (9,600 coulombs). And we got current 0.8 amperes. And our formula, wait, let me ask, what's the formula? Let me be nice and ask. We did that one in a previous past paper that we were doing. So let's see who remembers. Good. Q equals IT. Awesome. So finish writing my Q equals I times T. But they didn't ask us for charge. They asked us to calculate the time. So we transpose, divide both sides by current since it's multiplied by time. And so we get that time is equal to charge divided by current. So that gives us 9,600 coulombs divided by 0.8 amperes. What's that answer? Good, Kesia. Time is equal to charge over current. (9,600 divided by 0.8). 12,000. Awesome. Hi, Brisky. Thanks for joining. And you got that one right. 12,000. Unit? I'm not seeing any unit. We forgot our units. All right. Good, Brisky. I saw that you caught up on yourself. Good job. Remember, you have to use your units to get your maximum marks. Next one, calculate the voltage given that the power supply of the cell phone is 4.4 watts. Which formula again are we using? So they want us to calculate voltage, and they gave us power. Which formula can we use? Hi, Sean. Thanks for joining. And yes, your answer is correct. P equals IV again. A, remember, capital P. So P is equal to IV. They want us to find voltage. So we divide both sides by I. So voltage is equal to power divided by current. And that is 4.4 watts divided by 0.8 amperes. Answer. Good job, Casey. Good job, Chrissy. Right, we have what divided by charge too? So power divided by charge. Let's see. 5.5. Which one of the formulas you use, Chrissy? Let me see. Check your formula, Daryl. We could actually deduce it. But we're not going through that deducing. That's gonna. I could though. The W that you're using is not power. So that's the problem that you'll have with that formula. It's not power. Remember, the symbol for power is P. So that W is actually work or energy. Just I'm telling you to check your formula. So 5.5 is correct. Got that, Daryl? How will you find volts? Good. So we're moving up. Whoa. Moving across. Determine. Or were you giving me the formula for here? Which one was it? This formula now becomes applicable. I'm wondering if that's what you're giving me. All right, so determine the work done to fully charge the battery. So Daryl gave us the formula. V is equal to work divided by charge. So it simply means they want us to find work done. So let's start with what he has. Voltage equals, and is a capital W divided by charge. They want us to find W. So you multiply both sides by Q. This looks nothing like a Q, but it's a Q. So work is equal to voltage times charge, which equals 9,600 coulombs. All right, let's put the voltage first since that's what I have there. La la la. Voltage, what's voltage again? Voltage is 5.5, that's what we just calculated. Times 9,600 coulombs. What did you get there? 5.5 times 9,600. Yes, Casey, it's the same equation. Voltage equal energy over charge. Same thing as voltage equal work done over charge. Very good. Very good. So what's the answer when we multiply? So they want us to find work. So it's voltage times charge. What's the answer when we multiply 9,600 times 5.5? Good, Casey. So that's the answer I got too. But check your unit. Remember, the W is not power. W is work. The symbol for power is P, and we don't put the symbol for units in a formula, it's a symbol for the quantity. So check those units. So I'll write the 5,000, 52,800, but check that unit. Ah, awesome, Brisky. Awesome, Casey. So it's joules. Work done is measured in joules. And that's why we can say we can use energy or work, because they are one of the same. So that would be the answer to that question. 52,800 joules. The W is for work, because that's what they asked us to find, work done. So make sure that you are tidying up the unit part of life so that you're not getting, I need to get a picture for this one, so that you're not losing marks for units. So I want you to read this one. I'm going to get a pic for it. I need to get a pic for it so I can show you what's what. So figure 5 shows a solenoid that is connected to a battery with a current I flowing through it. So this is figure 5. Then figure 6 shows a cross-sectional representation of the solenoid shown in figure 5. The symbol, where am I? Dot with the circle represents the current coming out of the page. And the symbol X with a circle around it represents the current going into the page. Draw the magnetic field lines inside and around the solenoid on figure 6. So think about that. I'm going to go and get the diagram now that I need to show you. Or can somebody tell me the name of the diagram that I need to get to show? Let me see. Tell me what's the name of the diagram I need to get, or which diagram you think I'm looking at to get to show you whatever I need to show you relating to this question. All right, don't see any answer yet. Let me paste my diagram. What is this diagram representing? Awesome, Kenrick. Awesome, awesome. Right hand grip rule. Good. So that diagram is showing us the right hand grip rule, and we use this rule to determine the current. You will have the direction of the current flowing through a conductor, and you can determine the direction of the north pole. So you can use your right hand to determine the direction of the North Pole, and you can mimic it with the direction of the current, or tie it with the direction of the current. Very good. So let's look at this now. Let me explain, by the way. Based on how this hand is looking, if you hold a current carrying wire, or in this case, we're looking at a solenoid, if you hold your hand in the direction the current is flowing, so the current carrying wire, you're putting it in the direction the current is flowing. So your fingertips are pointing in the direction current is flowing. So notice that his hand is going this way and the tips are pointing in the direction current is going. So if you pretend you're holding the solenoid, your fingertips pointing in the direction of the current, then your thumb will show the direction of north. So fingers curl in the direction of current, thumb will show the direction of north. So now we have our solenoid here, and we have our current. This part is coming out of the page, so coming towards you, and this part is going away from you. So if we set our hands properly in the direction that is shown here, I'm going to try to find a diagram for that one specifically. Tell me which direction you will find north, whether it will be on the right or the left. Find one that shows current coming into you, away from you. But this one show you the north. Don't want it to show you the north yet, but I may not get another one that doesn't. La-da-dee. All right, so let me use this one. All right, so giving you 5 more seconds to see if I get a response. Where will the North Pole be? Oh, there you go. Waiting was good. North will be on the right. Excellent. So here's the diagram. This is how I want you to hold, quote unquote, air quotes, hold. Hold the solenoid. So your hand, your finger's going to curl in the direction of the current. So it's going at the top, it's going towards you. At the bottom, it's going away from you. So that's how your fingers will curl. Once you do that with your right hand, please, right hand. Once you do that with your right hand, north would be pointing over on the right side. So your North Pole is here, South Pole is here. What's the direction of a magnetic field? Relation to north and south. What is the direction? What did I ask about? Yes. What is the direction of the magnetic field? How you determine it? We spoke about how you determine the direction of an electric field. How do we determine the direction of a magnetic field? North to south. Good. Very good. Good, Kendrick. So, right. So, right, basically, it's a direction. So, you know there's nothing such as a monopole in existence in reality. In reality, there's no monopole, meaning you can't get a magnet that only has a north pole or a south pole. There is nothing named monopole. But to determine the direction of the field, you say, okay, which direction would a north pole move if I were to bring a monopole, a north monopole in that direction? Which direction is the field going to go if I bring a north monopole in the direction? So it's going to naturally repel because like poles repel, unlike poles attract. So it's going to repel. So it will move away or out from north and towards south. So now our diagram, the question says you must draw the magnetic field lines inside and around. Inside and around. So you don't have to put a lot. And then let me do this. I don't want to draw through the S. So we said it's going away from north. So we're going this way. Towards south, going this way. Away from north, going that way. Towards south, going that way. Away from north, that way. Towards south, that way. So once you indicate where your north and south pole is, or at least your north pole, you get your mark. You put your field around both, you get your mark. You put in your direction, you get your mark. And that would be your 3. That's how your 3 marks will be broken down. All right, so that's that for that question. Here's another question, and I need to get another diagram. The figures below show a constant magnetic field coming out of a surface as indicated by the symbol. And we know that symbol means it's coming out of the page or towards you. Figure 7 and 8 show a straight metal wire AB moving across the magnetic field in the direction shown by the arrows V. So we're looking at 7, seeing the direction of the conductor. And then we're looking at 8, with also seeing how it is turned. Continuing, figure 9 shows the metal wire moving parallel to the magnetic field. That is out of the surface. So in this one, the field is coming. I wish I could do something to show it coming towards you, but you get the gist. It's coming towards you, and the conductor too is moving towards you. So let me see how we apply the concept. Now, complete the table below by stating the direction of the induced current in the straight metal wire, AB, and how the magnitude of the current would change if the speed of the wire was doubled. All right. So, I'm happy I have both of them in my view. But I need to get another diagram. Need to get another diagram, man. Which diagram I need to get now? Which diagram you think I need to get? Fleming's rule? Be a little bit more specific. Little more specific, Casey. Don't want anybody to get confused. Left hand rule says A. Go again. All right, A says I don't know. All right, so Kendrick is telling us 90 degrees, right hand rule, thumb, index, middle fingers. That'll be the one. So guess what? How I try to remember it, or how I teach students to remember it. You have 2 rules. You have your right hand rule and your left hand rule. Separate from the grip rule. We're not even talking about grip rule right now. Separate from that, you have your right hand rule and your left hand rule. All right. And for those of you who I don't teach, I kind of, like I said, I use little things to help my students to remember these things. Sometimes it looks a little stupid, but it works. So generators induce current. They work from the principle of induced current. And motors don't deal with induced current. All right. So you have right hand rule and left hand rule. Right goes here. Left goes here. So actually I could motor effect. Yes. Left. So here's how I'm going to tell you to remember it now. Remember, generators work off induced current. So generators and induced current use the right hand rule. Look at my method now. Induced starts with I. There's no I in left. There's an I in right. Generator start with G. There's no G in left. There's a gene, right? You might be laughing, but yeah. The things I do to remember stuff. And then motor effect. You see, you can almost start spell effect right here. So EF. So motor effect uses the left hand rule. Tell me if that sounds like it can work, like you can remember it with that. How does that work for you? So, right, generators and induced current work with right hand. Motor effect work with left hand. Any takers? With this method, will you be able to better remember which hand goes for which rule? All right, well, I wait on your responses. We're going to work. Not seeing anybody respond yet. So, just get that down. All right, so I'm seeing the responses now. Motor effect would be for magnitude of current. So, hi, lovely Laugh Learn. Thanks for joining. So, you're asking the motor effect, you can use that here to determine the current. Both of them can use to determine current, but it's just which hand. So, for motors, there is no induced current in that, but the generators do have that. But for this question that we're looking at, it is a current that is being induced in the conducting material, which in this case is a wire, as it is passing through the magnetic field. So that's why you see me linking generator and induced current in one sense. So generators, they use induced current, but also in this scenario that we're looking at the current that is induced as a conductor is passed across or through a magnetic field. So A says yes, it could work. Okay, Miss. Awesome. Live, love. Love, live, laugh, learn. Awesome. So, going back to this one now. So let me go. Oh, I did not get the diagram. Let me go get that diagram. Right hand rule. Want to find. So basically, as who said it again? Kendrick said, when you are using this rule, whether it's right or left, your fingers should be set 90 degrees to each other, or we can say perpendicular to each other. And each finger shows a particular thing. So hopefully this diagram is doing justice. Hopefully this diagram is doing you some kind of justice. So when you do that, your finger here is pointed in the direction of the magnetic field. I think I can get a better one. Your index finger is current, and your thumb shows the direction of the force. Let me see. If I can get a better one. All right, so this one is a little bit blurry though. So thumb motion, first finger field, second finger current. Okay. All right, so let me use this one too. All right, so here is another one which actually uses letters from each finger to help you to remember what it is showing. So the M from thumb representing motion. First finger, the F is for field. And second finger, C from second for current. So that's another way you can use to remember. So thumb is showing motion. First finger field, second finger current. So now I want you to set your fingers in the correct way. So if it is coming out of the page, that's the direction of your field. So you point your, remember right hand now, point your finger in that direction. W is showing, what is W? Not WV. Hold on, wait. It says metal wire AB moving across magnetic field. Okay, so the V is showing the motion, so that's your thumb pointing in that direction. So thumb pointing up, your first finger pointing towards you, and your second finger goes in which direction? Use the letters A, B to tell me which direction, or you can say left to right, right to left. Tell me the direction current would be flowing through this conductor. So remember, first finger, your pointing finger, point to yourself. Your thumb pointing upwards. Which direction is the third finger? Your second finger. Which one direction is that pointing in? Sometimes it's going to be a little bit hard to configure your hand, I must admit, but you can do this. So try to do that. Right to left. You're using your right hand. And is your pointing finger pointing towards you? Thumb going up. Pointing finger turn towards you. Awesome. A and Elena, good. So pointing finger pointing towards you, thumb pushing up. That middle finger now is supposed to be going left to right. Awesome. Awesome. So if your index finger, that pointing finger, the finger you normally use, your pointing and say over there, so that is what is showing the direction of the field. So the field is coming towards you. So you point that finger towards you. The force is going up, thumbs up. So that middle finger is going to go left to right. Excellent. So we come here now, and it says in the direction of induced current. We can say A to B, you can say left to right. They didn't tell you any particular way to write it. They just said indicate, so indicate. Magnitude of current if speed was doubled. How does increasing the speed affect the current that is induced? All right, so, okay, so Live, Love, Learn is asking a question. Let me go back to this before I move on to the speed. How you know the field is coming towards you? Let's go back to the question. No, this circle and dot, and it's coming from over here. Circle with a dot always represents current coming out. So coming out of the page or towards you, whichever way you want to put it. Towards you or out of the page. So once you see a dot and a circle, it is representing out of the page. Once you are seeing a circle with an X, it is away from you into the page. So there's out of the page, dot and circle, X is into the page. That works. So as you notice, you're just seeing dots and circles, so it's coming towards you. The way they got this manner to determine or to show the correct direction, you're thinking of an arrow. So if an arrow is coming towards you, the first thing you see of the arrow is the point of the arrow. So that's why dot and circle or point and circle is used to indicate coming towards you or out of the page. If the arrow is going away from you, you will see a little X at the tail. So that would represent current going away from you. So that's the convention that they use to determine the direction or to show the current direction, the field direction. All right, good. So back to the next question. How does doubling the speed affect the induced current? What effect does speed have on induced current? How does speed relates? Anybody knows or remembers? How does speed relate to induced current? Tell me how. All right, so Alena said maybe the current doubles as well. And you would be perfectly correct. Yeah. So the relation between the motion of the conductor and the current that is produced, if you speed up your the motion or the force with which it is cutting, then you're going to include double or speed up your, or increase, not speed up, increase your current as well. So that's one way that you can change the current that is coming through. So you either can speed up. Is there another way that you can increase it? Or is there anything else that affects the size of the current that is produced? And I'm bringing it wide now, not just for a conductor passing through a magnetic field, but for a solenoid. A solenoid is going to cause induced current as well. So is there a way, or is there an effect, or what effect is there for it? So number of turns, good, very good. So Love, Live, Laugh, and Kendrick got that right. So if you increase the number of turns, you increase the induced current. Strength of the magnet, good. If it increases the magnet or the strength of the field, then naturally increasing the strength of the magnet increases the strength of the field, good. So if you increase that, you also get an increased induced EMF or current. And of course, the greater the speed, we cover that. And then the final one now is the type of core you use in the case of a solenoid. So if you use soft iron core, then that's going to increase it as opposed to if you use another type. All right, so that covers that. Let me go back to the question. So magnitude of current is speed is doubled, double. They didn't give us a value for current, so we can't write a value. We just need to write how it would affect it. All right, so diagram 8. Same thing. Index finger or first finger pointing towards you. The force this time is going to the right. What direction is the current flowing? Index finger towards you. Force or your thumb to the right. What direction is your current flowing? A to B. Awesome, Kendrick. Same A to B. And what would be the effect of the current? Same thing. Now, here's the final one. What happens if our conductor is moving parallel to the field? Can you even set your finger to represent that? Good, downwards. Okay, love, I see you got that. So, right. So very good, Elena. Hold on. So let's address this one. You say the thing turn, all right? So it's the same current towards you. So your pointing finger is still towards you, but this time your thumb is pointing to the right. The direction of the force is shown by V. Those two arrows are showing you how the conductor moved through the field. So your pointing finger towards you, thumb to the right. Where is your index? You're not index, your middle finger. Remember, all three fingers must be 90 degrees to each other. So they must be 90 degrees. Let's see, can I rotate this? No? If I could rotate this, I would show you. Maybe I can rotate it and bring it back. All right, let me do that. Let me rotate it and then put it back in here and show you. All right, so I'm going to rotate it. No, that's not the diagram I want. I want the last one. Where are you? Right here. So I want this diagram. So let me rotate it in the direction I want. So the force is going this direction again. I'm really not going to be able to. I just remember that it's 3D. I'm thinking of a 3D space. I'd have to use something like AutoCAD to rotate it or to have a 3D diagram in the first place to rotate it. So yeah, I'm not able to show it. I can't rotate it enough to show you. I can't rotate it in 3D space to show you. But yes, once you set your finger in the correct manner, you should get that it is going from A to B, which is down, flowing downwards. So I hope you are able to set your hand. Miss, but your thumb would point up. No. Let's look again. So this is the diagram we're using. This is figure 8. So we did figure 8. This is figure 8. So remember, your thumb is pointing in the direction of V. Your pointing finger, your first finger is pointing towards you. So where is your third finger? That middle finger, where is it going? Set your hand and let me know if you get it now. Remember, your thumb points in the direction of the motion for the conductor. Right, V is the direction of the thumb. Good. So when you get your questions, you have to check for which direction. So it says figure 7A shows a straight metal wire AB moving across the magnetic field in the direction shown by the arrows. So this one is moving in this way across the field. This one is moving this way to the right. For figure 8, it is moving to the right. So the conductor moving to the right across the field. So your thumb must point in the direction of right. Okay, you got it. Awesome. Good. And we got our answer for this one already. Let me just highlight those answers. Nothing, no current, no miss, no flow. No current will flow because the conductor is parallel to the field. And like I said, if you can't, remember your fingers are supposed to be 90 degrees to each other. There's no way for you to set the finger pointing towards you. That's your first finger. And then set your thumb, which is showing the direction, pointing towards you as well, and they're still at 90 degrees. There's no way for that. So that's another way for you to figure out and say, okay, nothing is going on here. No current is flowing. So direction of induced, no current. The magnitude, if speed is doubled, not an effect. Not a thing. No effect. So no matter if you double it, triple it, there will still be no current because the conductor is moving parallel to the field. So there will be absolutely no current going on there. All right. Let me see if there's any questions before I move on. All right. There was a question. Good thing I came back. Previous one. Thumb would be up. Yes. Yes, love. Previous one, the thumb would be up. Excellent. All right. So let's go to this question now. An ideal step-down transformer. So we did transformer earlier. So we're just doing another question on that. Reinforcing. So an ideal step-down transformer is used as part of a power transmission system. It has 1980 turns in its primary coil and 180 turns in its secondary coil. Calculate the maximum theoretical output voltage if the input voltage is 1320. So it says step down, so that means primary should be greater than secondary. So you just use that in case to verify that the values you write are correct. So I'm writing what we have. It has 980 turns in primary. So NP equals 1980 turns. NS equals 180 turns. So it is definitely a step down because it went from 1980 to 180. Calculate the maximum theoretical output voltage if input voltage is that. So VP is 1320 volts. So now we write our equation. They want us to find VS. That's what they want here. So we're going to write VS over VP equal NS over NP. If we want VS as subject, so if we multiply both sides by VP, it's going to cancel on this side. So we have VS equal to number of turns in secondary times voltage in primary divided by number of turns in primary. Substitute. Number of turns in secondary is 180. Let me check if there's any question while I'm going. All right. And the voltage in the primary, where are we? Voltage in primary, 1320 volts. Number of turns in primary is 1980. So turns going to cancel turns. So that answer, 180 times 1320 equal divided by 1980. Okay. Anybody got the answer? Awesome, Casey. 120 volts. Excellent. Next question. Calculate the input power if a current of 135 amperes flows in this primary coil. Let us just pause and make sure that our answer makes logical sense, by the way. It's a step down, which means voltage in secondary should be lower than voltage in primary. So see, primary voltage is 1320, and in secondary it's 120, so it's definitely step down. So you can do that to check to see if your answers at least make sense. So calculate input power. Formula for power, we've been using this so many times. So P equals, and I'm going to put a subscript P here for primary. We've used it many times since this evening. We start writing. Thank you, A. Voltage in primary. Good job. So they gave us the current in primary. So that's 135 amperes times the voltage in the primary was 1320. So that answer becomes 135 times 1320. 178,200. Awesome, Casey. 178,200. Unit watts. Good. We are remembering our units. Awesome stuff. So A gave us the formula. Casey gave us the answer. Awesome. And we finish another question. Wow. Not bad at all. We're not done yet though. We have 2 more questions to go. So I foresee us finishing up about 9:30. That's 45 minutes. This question is not difficult, so we can run through this one pretty quickly. Logic gates, yay. And this one is from the January 2020 paper. It's question 5. So now they want us to complete table 2 by inserting the missing logic gates, symbols and functions. So we are going to put in the logic gate, the name of it. So the function is it changes logic 0 to logic 1. Which gate does that? Which gate does that? Awesome. I'm seeing Chrissy. Yes, Chrissy, it is a not. Casey is saying not. And Elena saying not. All correct. It is a not gate. So we put our name here, not. And the symbol is a triangle with a little node here. And it has one input. One input, one output. So that's our inverter, and otherwise known as our NOT gate. I had to take a water sip just now. All right, so the AND gate. What does the AND gate look like? And what is its function? How does it work? So being that they gave you this as a sample, you can use that. So produces, for the NAND gate, they said produces a logic 1 only when A and B are logic 0. So we will write the function in that manner. So what does the AND gate looks like? Charger plug. Awesome, Chrissy. All right, so let me tell you how I tell my kids now. The AND gate looks like a capital D. And D for AND. D is in AND. No, this one looks right. That looks crooked. Let's straighten it up a little bit. So it looks like a capital D. All right. Okay, very good, Casey. Casey broke it down for us. You get 1 as the output if 1 and 1. That means if both inputs are 1, you get 1 as the output. So if you have one input being, what did I just say? That's so wrong. Let's go again. You get 1 as the output if both inputs are 1. But if you had a 1 and a 0, it's going to be 0. 0 and 0, going to be 0. Very good. Elena, if 1 is in the input, all right, so Elena, yours needs to be edited a bit. The AND gate produces 1 or a logic 1. Put the 1 in here, so only if A and B are logic 1. So another way how I go through with this as a logic gate, telling them how it functions. The AND gate, the only time you can get a logic as 1, or the only time the output is 1, is if input 1 and, emphasis on the and input 2 is 1. So that's an AND gate. You only get a 1 if input A and input B is 1. The OR gate now, how this one, emphasis on the OR. Tell me the logic or the function for the OR gate. So let me start by saying produces. So emphasis on OR produces a logic 1 either of the 2 inputs. Excellent. Very good, love. So the OR gate produces a logic 1 if one logic is 1, it produces, awesome. It produces a logic 1 if input A or B is 1. Excellent, Casey. And Casey is breaking it down for us again. So 1 and 1 equal 1, 1 and 0 equal 1, 0 and 0 equal. Casey, I check that one. And that's your OR gate. Now the NAND gate, notice it has awesome A. So notice the NAND gate, it has AND in there somewhere. So it's going to look like the AND gate somewhat, but it's going to get this as a node. And that's where that becomes now our NAND gate. So it's going to look like the AND, but the node makes a distinction between AND and NAND. And that completes that part of the question. Next question. This one is looking at rectification. Good stuff. So with the aid of a circuit diagram, describe how an alternating AC, alternating current. Awesome, Casey, good. Describe how an alternating current can be halfway rectified to produce a direct current across a resistor. So it says you are to use a diagram. It says with the aid of a diagram. So please, you cannot just draw the diagram to get the full marks, nor can you only explain to get the full marks. It says with the aid of a diagram. So there must be some description and there must be a diagram. Both has to go together. So we are going to, and it's specified a circuit diagram. So you can't just draw any and any whole diagram. All right. So yes, love. A laptop charger would have this application true. So what we mean when we said something is rectified, by the way. If it's rectified, what does that mean? The process of rectification is what exactly? Right, love, very good. So the rectification will take place in that part, right? That's not the only part in there, though, but there's a diode in there that is doing the rectification. And he would have answered the question I asked too, meaning I asked what is the process of rectification? Excellent. Converting AC to DC. And just another quick concept check. I know we did the transformer some moments ago, but does a transformer ever have DC on the primary side? So we're just backing up a little bit. Does a transformer ever have DC on the primary input side? Why or why not? So while you answer that, I'm going to be drawing the circuit diagram. Oh, wait a minute, this one. So that's the question. Does a transformer ever have, or can it have, a DC supply in the primary? And it says across the the resistor. So we're going to put the connection right here. So I'll look for the answer and I'll highlight it when I see it. Does a transformer ever have DC in the primary? And you can tell me why or why not. Okay, so now I'm going to describe how an alternating current can be halfway rectified. So when the circuit is connected as shown, current will flow through the diode when it flows in the positive direction. And we would remember that alternating current means it is going between positive and negative. So the current will flow in the positive first, then it will change and go in the negative direction. So when the circuit as shown is connected as shown, current will flow through the diode when it flows in the positive direction. However, when it flows in the negative direction, no current will flow. It will flow through the diode and so no reading will be displayed and the negative signal, or as the negative signal, is said to be clipped. Right? So you could also include the terms forward bias, reverse bias. So when the current is flowing in this direction, it would be in forward bias. So current will flow through, a reading, the circuit would be closed, a reading would be registered on the oscilloscope that will be out here. When the current now change direction and is going in the negative, no current will flow because no current will flow in this direction across the diode, and so no reading will be registered. So that means it will be in reverse and no current flows in that way. So once you draw your diagram and you give a good description, you mention that current will flow, the positive will flow through the diode, and you can mention forward bias, and you mention that in the reverse, the negative will not flow through it. Good. And once you mention those terms, you will get your maximum marks. So that is 5, and we would have gotten it. So I'm not seeing any answer for my trivia question. This is 5. Not seeing any answer to my trivia question. So let me just tell you what's up with that. You don't and you won't have a primary input on the side on a transformer. You can't have a DC, you can't have a battery connected to a transformer for you to get it being functional. Reason being, with DC current, no current will be induced in the secondary coil. So remember that the transformer works from the principle of induced current. So the current would be on the primary coil, and then as it reverses direction, it will induce an EMF in the secondary coil. So if there is no change in direction in the primary, there will be no induced EMF on the secondary. So the answer to that is no, you will never see a primary input for a transformer that works at least. You will not see the primary input being a DC for a transformer. All right. So now we move on to the next question. It says sketch the voltage time graph to show the expected output across the load in B1. So another thing you could have done in your question, not a must, but you could have just put a diagram here somewhere and show the input signal. CSEC AC input. As I say, you don't have to. So this is what the signal will look like that's going into the system. So you will have the AC flowing in positive and then going in negative, positive and then negative. But when it has undergone or gone through the diode, the negative will get clipped off. So all you do, you just simply draw the positive sections. You know, the negative will be there, but it's clipped. You come a positive again. Negative is clipped, positive. So that is the expected output once your diode is working properly. Next question. Next trivia question. Awesome 8. It'll only be positive. Next question. What was the question again? Hold on. Wait. The question just slipped me. Wait. Let me look at the diagram. Oh. If the diode is not working properly, how would you know? Or let me rephrase that question. How can you test if a diode is working properly? How can you test if a diode is working properly? All right, waiting a few to see if I will get an answer. If I don't get an answer, I'll give you the answer. So while I wait on that answer, being that it's a side question, I'll work on this now. So it says, draw a voltage time graph showing an AC source with a frequency of 5 Hertz and a peak voltage of 12 volts. All right, so let me see. I see an answer coming in. Connected to an oscilloscope which display. Oh, let me check the laptop. Right a bit cut off. Connect, which will display the appropriate sine wave. Awesome. So that's the beginning part. That's the beginning part. So you set it up in the circuit. You can do it in the circuit like the one I drew. And you're checking for the wave. So how will you know? What will tell you if it is working or not? So you set it up, you see the wave. What will you use to tell you if it is working or not? Going to this one now. Draw a voltage time graph showing an AC source with a frequency 5 Hz and a peak voltage 12. Okay, so for this one, it's telling you frequency and peak voltage. Oh, Lord. How when you don't. Ah, wonderful. So, first off, this is a voltage time graph, which means you need to calculate the period from the frequency. So, remember, frequency equal 1 over T and period equal 1 over F. So we do our calculation. Period is going to be equal to 1 over 5 Hertz, which is equal to... Did I get another answer? All right, so not A, case here. If the, oh yes, I saw our A, I'm seeing your answer no. If the current flows in one direction, only good. So let me give you the full answer or a complete response. So putting case here, A and Elena's answer together. If you connect the circuit as I drew in the previous question and you connect it to an oscilloscope, you put your diode, let me go back over to it. So you put your diode in one direction. Put it in this direction, check the reading on the oscilloscope, check the output signal that you're getting. Then you would turn it around. So you turn it. Remember, you're not going to see these things on it, you know. So you can do one of two things. You can check to see if it's conducting in both directions, or you can also turn it around and see if you will get a reading. See if you can. So depending on the type of diode you have too, you can do the test. So you put it in one direction, see if you're getting a reading, then put it in the other direction and see if you are getting reading. But once you connect it to an oscilloscope and you are seeing if you're getting this clipped look like we have down here, if you're getting the clipped look, then you know that it is definitely working. But if when you connect your diode, you will get a full reading, then that means it's not working. But you have to turn the direction too, so that you can make sure that it's not you connecting it wrong. If you see no reading, you turn it around to see if it's you connecting it incorrectly. But once you are getting reading, it should only be half of the reading. Shouldn't have a full wave going there. So that was a sidebar. Back up here now. So they say we should draw a voltage time graph to show frequency 5 Hertz, peak voltage 12. So 12 is here. So that means our crest should be here. Our frequency that we calculated is 0.2 seconds. So that means our wave should end here. Remember, the period is the time taken for one complete oscillation. So we go here. It also means that the crest should be here. And trough can be there. So let's go up. Hold up now. So again, crest should be here actually. Here, and trough is going to be here. so that you can complete in point 2. So you go up to crest, down half a wave at point 1, down and up 1 wave. If you want to do it again, so crest should be here, trough should be here. I'm going to erase that mark that I put first. So crest, middle here, trough here. Let me fix that. Point 4. So it gives you the peak, so you cannot go beyond the peak. Make sure you stay at the peak. So 1 complete oscillation, you're starting at the beginning of a crest here. So by the time you get to 0.2 seconds, you should be starting another crest. And that would be the period, the time for 1 complete oscillation. Right? So that basically does it for that question. We're done that one, and we have 1 more to go, guys. Just 1 more question. All right, awesome, Chrissy. Awesome, Casey. So 1 final question. And this one has to do with the motor. So like I said, I would have chosen questions so that you got a good mix of electricity and magnetism. So let's go through this one now. So this question is one of those that you have to write on one of those back pages. So I'm going to create our back page. So it says, with reference to the diagram of a simple DC motor shown in figure 2, explain how this motor works. So let's examine the picture before we get any further. You have your magnet, North Pole, South Pole. You have your coil in here, split ring commutator, your carbon brush. You have your switch here, rheostat, variable resistor, and your power source. Now, just a reminder, a motor converts mechanical energy to a motor converts electrical energy to mechanical energy. So the electrical energy that it's getting, the electricity it's getting, will be converted to mechanical, some movement. So that's why now for the motor, you connect a battery to it, and then you will see the part at the top there start spinning. That's a motor. It uses electrical to give you mechanical. Okay, so explain how this motor works now. So earlier, we would have looked at 2 rules, right hand and left hand. Which rule applies to the motor? Awesome, Elena, rotational, good. Which rule applies to the motor? We did 2 rules, left and right. I told you that the right hand rule is for one thing, left hand rule is for another thing. Left hand, excellent, very good. So Elena got it and A got it. Kendrick got it too, awesome. So the left hand rule, because remember, we use the EF for left to match with the EF for effect. So it's called motor effect. Very good. So how this motor works now? All right. So you're going to have this now being connected. Remember, you're going from electrical first. So you have your battery and you connect. Now notice, let me zoom in a little. Like I said, this is called a split ring commutator. So here is the gap for the split and here's another one. In this current setup, however, the commutator is in contact with the brushes. So once that is happening, after you close your switch, there will be some movement here. But we're going to have to determine how this movement is going to work. Let me get the left hand rule pick. All right. So with the left hand rule, it is the similar concept to what we did with the right hand rule, but it's just that we're using the left hand. So the thumb still represents force. The pointing finger still represents field. And the middle finger still represents current. So that's your left hand rule. So now we want to determine which direction this coil is going to be turning. We want to determine that. So when the current starts flowing, this is the positive side of the switch. So we're going to flow this way. Remember, even though we have that current flows from negative to positive, meaning electron flow, when we're dealing with circuitry and we deal with conventional flow. So you will always see positive to negative on your diagrams. So we're saying current is flowing this way. So it is coming this way through the coil and coming back out this way. So we now need to determine which direction this is going to spin. So get your left hand, put your which finger? Pointing finger in the direction of the field. Remember, the field moves away from north. Middle finger is going to go in the direction of the current. The current is going away from you in this scenario. Which direction is your thumb pointing after you set your finger like that? So going again, your thumb must be pointing to south, not your thumb. Your pointing finger should be pointing to the south. Your thumb, before we get to thumb, your middle finger is pointing away from you because that's where current is going. Which direction is your thumb? And so which direction will that part of the coil move? So we do that. I'll start writing some points, and I'm going to write it in point form. Which direction is your thumb pointing? Downwards. Excellent. Good job, Elena. Good job, Kendrick. Good job, A. Very good. So yes, it is pointing downwards. And you recognize that based on this arrow, this is showing the direction of rotation, It's going down. Very good. And that means so this side, do the same thing. Pointing finger pointing to south. Current is now coming towards you. Where is the thumb going? Upwards. Excellent. So this part is going up, this part is going down. So you're getting that kind of rotation. So for this one, the motor will be turning anti-clockwise. Very good. So we're explaining how this works now. So when the switch is closed, it's A1 that we're doing. When switch is closed, let me get some more space. When switch is closed, current will flow. I left off current. Current will flow as shown by arrows. Will flow through A, B, C, D as shown in the diagram. Right? Then the next point, we know that there will be a force on the coil because it is cutting the magnetic field. So that's 2 is important. So that's how you're getting your force. So since the coil, it cuts the magnetic field, it will experience a force. It's going to experience a force. So for side AB, and this is a 5-mark question, so you know there's no diagram that you're going to put in this one, so you got to write. For side AB, the force will act downwards. And if you want to show them, say, hey, I know what I'm talking about. You can say based on Fleming's left-hand rule. Wait. And side CD will move upwards. Causing the coil to turn anti-clockwise. Good. So we're going again. When the gap in the commutator makes I can't say makes contact because it's a gap. Can't make contact. So it does not say that. When the gap reaches the contact brushes, no current will flow. Because the circuit is open. However, let's make this a capital H. However, the coil will still turn due to its momentum. And you know, Newton's first law tells you about the laziness or the reluctance of a body to have its motion altered, known as inertia. So because of that, it will still turn. So now let me get more space. The whole heap of writing. 5 marks, guys. We gotta get our 5 marks. So AB, once that happens now, so let me go to the diagram. Show what's happening here. So look at it now. So when it makes a rotation, so it rotates to this point where the gap is now at the place where the brushes are. That would have been a half turn because you know this is half, this is half. That would be a half turn. So now AB would be over here, CD would be over here. So the current direction in AB will be different. Because remember, AB is going to be over here, and now the arrow will be going this direction. So it's not the current that is reversed, you know. It's not the current that's reversed. Remember, this is a DC system. It's not the current that is reversed. It is the current that is flowing in the particular side of the coil that is changed. So because there's no change in the direction of the current, it will continue to turn in the same anticlockwise direction. Because if you notice, your motor is not turning clockwise and anticlockwise, clockwise. No, it's one motion. So please be careful. Do not say the current is reversing direction in the coil. You have to be specific to say it is reversing in the particular side of the coil. All right? Where was I? Due to its momentum. So we say now AB and CD will now be on opposite sides. And so the current in each will be reversed. So AB will now move upwards and CD will now move downwards. But the coil will turn in the same direction. Will not T. Will turn in the same direction. And that rounds up our 5 marks. It just hit the 5 mark. So the key things that you have to ensure you say, let me highlight them. Key things to put. So the key things to say, you can start off with the switch being closed and current flowing as shown. Then you may or may not talk about the fact that once it's cutting, there's a force. But you must say AB moving downwards and CD moving upwards and say which direction it is turning. Then you have to mention about the gap reaching the contact brushes and that no current will flow. And you have to mention the part that, oh, I have 2 wheels here. However, no, this is coil. You have to mention that the coil will still turn due to its momentum. Then you have to mention that they're on different sides and the current in each is reversed, but the coil will turn in the same direction. Those are some of the key points that you must have to get your maximum marks for that question. Okay, guys? So we just did that one. Luckily, or don't worry, this question, only that part was a long writing part. You don't have any more long writing to do. So we would have just got our 5 marks. So that's our 5. Now we're going to A2. Give the purpose of the commutator. So the purpose of the commutator, B2, the commutator reverses the direction of the current in the coil every half turn. That's the purpose of it. All right, so we move to our next question now. All right, so A is still following me. Awesome. I hope the rest of you are still following. We said 9:30, it's 9:36. You're almost done. Don't worry. Almost done. We're not going to make it up to 10. We'll be done before that. All right, so the next question now says, skip back over to it. A 24 DC, let me zoom. A 24 DC motor was used to lift a small appliance of mass 25 kilograms from the ground to the second floor of a multi-story car park. The floor is 30 meters above the ground. The motor, operating at 100% efficiency, works at a steady rate and takes 5 seconds to complete the activity. So for a motor, 100% efficient means work input equal work output. So where are we? So we're going to record what we got in the question. I need to zoom out a little bit still. All right, so this is B. B1. We're going to record. So we get voltage equals 24 volts. We get mass equal to 25 kilograms. We got height. Can you see which can you still with me? Good. Can you see which formula is coming out already? Height is 30 meters. And time is 5 seconds. And they want us to calculate the power provided by the motor. So let's go here. So which formula for power? A, you almost get it, almost get it. You get the energy part. But what's the formula for power? Power is equal to what? So mgh is the potential energy, and that is the work that was put into the motor. Okay, good. Work over time. Very good, or energy over time. So A does fix that part of your formula. You have everything else good except you left off time. So because they mentioned the part that is 100% efficient, it simply means that all of that energy that was used to lift it is what was used to carry out the function. So all of the energy in is equal to the energy out. So we're going to put energy over time. So power is equal to mgh over T. And for this one, how much marks was this one? Let's see if they want you to mention that part. It's 4 marks. Very good. So that means they want you to mention how you're getting this mgh here. They want you to tell them. So you're going to say, since motor is 100% efficient, then you can say work in equals work out. So that 4 marks, they wouldn't give you 4 marks for just doing, they want you to put that part. They want you to show why or how you're getting that energy. So you put that now, then you say, okay, power equal, we're going to substitute because we have the formula already. That's what, ooh, what is happening here? Let's go again. 25 kilograms times, we know that gravity is 10 newtons per kilogram. And we know that the height was 30 meters. So mgh, and then over time, which was 5 seconds. No, that is 5. Oh, we may get to 10 o'clock. It's 9:45. All right. So that's that. Into that goes 5. And then work out the rest of it for me. So 5 times 10 is 50. 50 times 30 is... Excellent, Kendrick. Very good. That'll be my answer. 1500 watts. All right. So that's your 4 marks. Tell them that, hey, I know what's going on here. You can't fool me. All right. Next question now says calculate the current drawn from the DC supply. And this is naturally going to be the same formula we've been using all along. Not energy over time, no. Same formula we've been using all along. So that's 2. And if you want for this one, you can also state that since motor is 100% efficient, power in equals power out. Doing these things really show that you know the concept. So we're using the same formula. Yes, AP equals IV. But they asked us for the current. So we divide both sides by V. We get current is equal to power over voltage. We just calculated the power. We had the voltage, was the voltage 24 volts. So the power was 1500 watts divided by 24 volts. Good job, Kendrick. 1500 divided by 24 gives you... Start right. Ah, good job. 62.5 amperes. Good. I'm seeing my units. Yay. Good stuff. Almost done. We're almost done. We're almost there. And this question is a one more question. Yay. If the power required to lift the appliance was greater, what effect would this have on the value of the current? Assume the voltage rating remains constant. I think we covered something similar to this since night. So if power is greater, voltage is staying the same. So let me underline that. So the things they put at us, they say if power required was greater, voltage remains the same. What effect are you going to have on current? So we can just simply, if we really don't remember the answer for this, we just simply look at our formula. All right? Putting this one in red. So we say, all right, I know that you're in the exam and you're reasoning to yourself. I know that power equals current times voltage. I know that for a fact. Now they're asking me what effect it have on current. Okay, so power is increasing, but voltage is the same. So let my formula be written in voltage. So voltage would be equal to divide both sides by current, power over current. All right? And my voltage is supposed to be the same. So my power is increasing. My current is what is happening to current to get voltage. And if you see the formula, but you still cannot get a sense of what will happen, it's always good to just throw in some numbers to test. So you say, okay, what was the power in this one? Power was 1500 watts. And if they say, and the volts is 24, so you plug in your formula and you say, okay, you want to find current. So you're going to write it in current now. Current is equal to power divided by voltage. So you say, okay, I want to see what happened to current. So when my power is 1500 watts, my voltage is 24 volts, I'm getting this current. So let's see now, I'm going to increase my power because they say power is greater. So let's put my power at 2000 watts. And they say voltage remain the same, so it's the same 24 volts. How will that affect your current? So you say 2000 divided by 24. You're getting that the current is 83. 83 there? Looks like 83. 83.3 amperes. So you try that and you say, oh, I see. So when power increases, if voltage is the same, current must also increase. And that is a way to get your answer. So if you end up in the exam and you cannot remember the concept, if it's a formula that you can plug values in, you just plug your test values. It doesn't have to be that the question gave you the values. No, you can just look at the concept, what it says, and just test it and see what is happening. So you get that the current would be greater. And that is the answer. So what was that? B3. So let me write it here. If power would be greater, but voltage remains constant, then the current would increase. And there you just got your 1 point. And that is that. And you are done. So this is your 1 mark naturally. 1 mark here. And again, like I did for the first question when I stated, you see the fact that this is a 4 marks question, it means that something extra is going to be done. So generally, calculation questions are 3 marks. 1 for formula, 1 for correct substitution, and 1 for the answer with the unit. You see, if you're seeing a calculation that is worth 4 marks, it means either you're going to have to calculate one of the values that you need, or you're going to have to, let's say, like the one earlier where they asked for the, what was it, the time in seconds, and they gave us in milliseconds, right? So it's either you're going to have to convert something or calculate something else or write something. So once you're seeing a calculation being a 4 marks, just think, what is that additional mark that they want me to put? And then you can get your answers and get your full marks. And that is it. That's the final question I had. Yeah. So we did 1, 2, 3, 4, 5, 6 questions in the time. Awesome. 6 questions were done. And so we have come to the end of this live stream. We are beating the 10 o'clock mark. Awesome. I just want to say thank you guys for staying with me throughout this live. I really do hope that what we would have gone through would make it much, much, much easier, much better for you to master, go through, and just ace up your exam. Please remember to get some sleep. Remember, I told you the story with me, not getting sleep and sleeping in my exam for half hour. Please, please, please do not let that happen to you. So, get some sleep. I know you might want to get in some additional notes or additional stuff for the exam, but please get some sleep. All right. All the best for your exam. Thank you again. Love you guys. And when you get in the exam and you just imagine me smiling with you and like, yeah, you got this. My kids who know me know that I'm like that. Like I'll be there and just thumbs up. You got this, guys. You can do this. Go and pass your exams. Thanks for joining once again. See you guys whenever I do another live. You've been a great audience. Bye, guys. And I'm going to do my regular. This live stream you're welcome, Kenrick. I've been saying Kendrick, haven't I? I'm so sorry. Kenrick. I'm now seeing that it's Kenrick. This live stream, let's go again. This live stream will end in 5, 4, 3, 2, 1. Bye.